Recording is on, so we're ready to get started. Okay, welcome back, everybody. We're going to continue from where we left off, but I just want to point out a couple of things. So first of all, I sent a note to everyone about the YouTube site, and so the links to the YouTube site are on the Sakai page and the Moodle page. So you can get the recordings there. If you want to subscribe to the YouTube channel, go right ahead, or just use the link to go there if you need to view any of the videos. Also, the annotated notes from the classes will be plugged in here on the schedule listing as we go. Okay. Assignment 1 is active in the sense that, you know, we've covered some of the material you need for assignment 1. It's due in a week. You can get to it right here. There's also a data file to kind of go with one of the problems there. Well, not much else to say about that. So, okay. I think that gets us up to date on the general information. So let's see where we were. Okay, so where we left off last time, we basically were talking about some things that kind of go back to linear systems material and things like that, but kind of, you know, again, in your typical undergrad engineering linear systems class, they're really only talking one-dimensional. And we're talking 2 or more dimensions here, but the concepts are the same. They just extend and have different names. Okay, and so part of the language, you know, part of this is the language of the field. So we talked a little bit about, you know, what it means to be a linear shift invariant system. And I wanted to go back to this to kind of reemphasize the language, right? And so the point being that if you have a system and you know its response to a unit impulse or delta function, or it probably has some other names, then you know everything about it if it's linear shift invariant. Okay, that's everything you need to know to be able to calculate the output for any input, to perfectly model the system. And so in this case, you know, we have a point here as input. This is the 2-dimensional equivalent of a delta function displayed as an image. Sometimes that doesn't come through very well in the display. We'll go a little bigger here. And then that passes through the system, and at the output we see something that is not a point anymore, that's been blurred, etc. And so because that expresses what the system does to a point, we usually refer to it as a point spread function in imaging, okay? Or PSF. And so that's language that I will use probably quite a bit. And of course, because it's shift invariant, if I move this point anywhere in the field of view, I'm going to see the same output, just move to a different place in the field of view. Okay, so that's one thing I wanted to return to. And then, so again, back to the idea of comparing, you know, 2 point spread functions. The idea is that the point spread function expresses how much blurring there's going to be in the system, right? And so the implication here is, although I could be playing display tricks on you, I'm not, okay? I'll talk more about that later. System 1 has a narrower point spread function than system 2. And so the blurring in system 1 would be less than in system 2. And so if comparing, say, 2 outputs from the same hand radiograph as input to those two systems, the one that is, experiences less blurring and therefore retains more detail, has better resolution. There's a lot of different ways of saying it, has more high frequency content. We'll talk about that. System 1 would correspond to this output versus system 2, which has, again, more blurring, less detail, would correspond to the wider point spread function. Okay. So point spread function is one way of talking about resolution, which is a thing we're going to discuss a little bit more later today. Okay. And then, there's well, we started just talking about the Fourier transform, but, again, as I said, we're not going to be doing a lot of Fourier transform math. We're going to be using it kind of qualitatively to kind of express things in the frequency space that the Fourier transform, gives us a link to. Okay. And so, again, this is just a way of expressing the two-dimensional Fourier transform. If you're used to the one-dimensional Fourier transform, it extends pretty readily. Again, you can implement a two-dimensional Fourier transform by taking a one-dimensional Fourier transform, say, along the rows, and then a one-dimensional Fourier transform along the columns. So you can do it as two one-dimensional transforms. And the same, if you're doing a 3D Fourier transform, you can break it up into three sets of one-dimensional Fourier transform. In fact, that's generally the way multi-dimensional Fourier transforms are actually implemented. Okay. So, so mathematically and kind of qualitatively, and what this does is no different than what was kind of expressed back in one-dimensional Fourier analysis. This basically takes your image and converts it into a different space where the image data is expressed in terms of, in this case, spatial frequencies. Okay, and so there will be high frequency, low frequency content, and the general idea is that, okay, any image could be one of these. Any image can be expressed as a set of pixels. That's one way of expressing it, but it can also be expressed as a set of frequency elements, frequency basis functions, each of which is different and orthogonal to the others, as basically this image could be a weighted sum of all of those different frequencies. Now, these are going to be two-dimensional frequency basis functions, but they still look like complex sinusoids. They just tend to, well, if you displayed them, they would look like kind of stripes, essentially. But if you took a profile through, it would look like a sinusoidal function expressed along any one of the dimensions, but in different frequencies, meaning some of them, complete one cycle across the image, 2, 3, 4, etc., cycles across the image, and at different angular orientations because of the X and Y frequencies. But that's basically what we're doing here. We're expressing a way of breaking down an image into a weighted sum of different frequency elements. Okay. And as noted, the units are no longer hertz, right? Because that's cycles per second. Now we're talking about cycles per distance of some kind. So cycles per centimeter, cycles per millimeter. It could be cycles per pixel, because a pixel is a unit of distance in this case. And we could alternately use radians, although more typically we talk in terms of cycles in imaging. Okay. And then we kind of left off here with the idea that, okay, yeah, if I have a linear shift invariant system, then I can get the output by convolution, and I don't have to do anything with Fourier, right? If I wanted to do a two-dimensional convolution, I could. Well, you can do it in MATLAB, okay? Or an alternative to that is to take a Fourier transform of the input image, multiply it by the Fourier transform of your point spread function, okay, and then invert the Fourier transform of the result. Okay, and again, as I said, if you have a physical linear system that's linear shift invariant, it's not like it's doing this unless you're actually using Fourier optics to do it, okay? But this is an equivalent model for what it's actually doing, okay? And so as a result, we have an alternative here, right? Remember, we said the point spread function expresses everything you need to know about the system. Well, it's got a unique Fourier transform also, and so its unique Fourier transform expresses everything you need to know about the system in a different way. And so if you know this, the point spread function, you know this, because all you have to do is take its Fourier transform, and vice versa, okay? And so in the frequency domain, we refer to that, again, by a couple of different names that are a little different than what you find in 1D. In one dimension, you could call it the system frequency response, and that applies here, or the transfer function of the system. But for whatever reason, this terminology has stuck. The optical transfer function, even if it's not an optical system, or OTF, basically is just the Fourier transform of the point spread function. Okay. Now remember, this is complex valued, right? It's a Fourier transform of a thing that is presumably real, and so we get real and this has real and imaginary parts. And so if we only care about and this is often true in imaging, we often only really care about the magnitude of that thing. And so the magnitude of the frequency response. In other words, how does it take an input frequency and scale it? Okay. Then the modulation transfer function is usually expressed this way, and also often normalized to the zero frequency result. The reason for that is a lot of times in imaging, we don't care about absolute gain of the system, because you can always kind of manipulate that when you actually display the image. Okay, I'll be a little bit careful of that, because sometimes in some applications, absolute quantitative values are meaningful in imaging, okay, depending on your measurement system, and sometimes they aren't. And sometimes the values you get, don't mean anything physically. It just displays an image so that you can see stuff. But the MTF is usually, you don't really see optical transfer function all that much, at least in medical imaging. MTF you do see people refer to. And so that's just referring to the magnitude response of that thing. There is a phase component to that, the phase transfer function. But for the most part, when we're dealing with real valued images, the phase transfer function only impacts shifting locations and things like that, and we don't usually worry about that all that much. Okay. Again, this is true in most of the medical imaging things that we're interested in, although some of the ones that don't acquire data, let's say in a kind of direct two-dimensional or three-dimensional form, such as ultrasound, MRI, and a lot of optical methods, you might be a little bit more concerned about that. So I'll kind of qualify a bit with that one. But for our purposes, a lot of what we're going to talk about is MTF. Okay, so all right. So if I was to compare two MTFs, and a lot of times if you take a two-dimensional Fourier transform, it's going to look something like, it's going to have a four-corner display where zero frequency is up here. Okay. So, and then there, because this is a discrete system, there's a redundant part here. And so this quadrant is the unique part of that Fourier transform. You can think of this as the negative frequency side, which has to have some symmetries if our, if things are going to be real valued back in the spatial domain. And so if we compare two MTFs, okay, and look at system A and system B here, basically what are we expressing? Well, and by the way, this is just a profile drawn along this axis. Well, we're expressing the system's response. In other words, if I input a certain frequency, the output gets scaled, right? And in this case, since everything is less than 1, the output gets attenuated, okay? But different frequencies get attenuated in different ways. That's basically how these systems operate. And so the idea here is that as we go from 0 out to higher and higher frequencies, right? If you think about, this is in terms of cycles per pixel, okay? But let's just say we had 1 millimeter pixels, then this would be cycles per millimeter. As you get to more and more cycles, here, let me bring out my tablet here. Okay, and so, if you think about the fact that we're expressing different frequencies in the form of sinusoids, and if this is, I'll just use as an example, a distance of a centimeter, right? The higher frequency has more details, of course, and therefore is able to, express things to a, let's say, better resolution, in the way we usually think of spatial resolution. Or another way of looking at it, right, is that if I want to express something with a lot of detail, then it's going to have some components of high frequency in it. Okay, if my system is not responsive to high frequency stuff, then it's going to limit the amount of detail I'm going to be able to have in the output. Okay. So if you compare these two, you notice that the blue case, I guess system A, has higher responses at least these mid-range frequencies, right, as compared to system B. And so as a result, system A would allow more high frequency through the system and therefore would provide more detail at the output. And if you think back to, what difference, how does that work in response to this? Well, those MTFs are the Fourier transforms of these guys, right? And so system 1 was very narrow, system 2 was very wide. Well, when you take the Fourier, if you'll know this from my class, those of you who took my signal processing class, right? If you take the Fourier transform of something narrow, then it becomes wide in the frequency domain. And if you take the Fourier transform of something wide in the spatial domain, it becomes narrow in the frequency domain. There's this opposite relationship between spatial domain and frequency domain. We see that, and these are Gaussian shapes, so the Fourier transform of the Gaussian works that way. Okay, well, if I think about that, then this one will have a wider Fourier transform, wider MTF than system 2. And so if I come down here, and in fact, these are, I think, the Fourier transforms of those two things, then what we have here is actually, this is system 1, and this is system 2. Okay. So the point here is we can look at this in a couple of different ways, right? You can look at it as PSFs in the spatial domain and say, okay, how much blurring are those things going to do? Or if we Fourier transform them, we can look at them in terms of MTFs and express it in terms of, okay, what's the frequency response? Which one admits more of the high frequency content than the other? There's just two different ways of expressing the same thing. Okay. Does that make sense to everybody? Any questions? Okay. All right. So here's the key point, right? Small features in an image require high spatial frequencies. Okay. And so as a result, a system with a lower MTF at the high frequencies, such as system B here, okay, or system 2, as in this case, is not able to retain the detail of the original. Okay, and so, you know, if we looked at, I didn't do this, but if we looked at the frequency content and compared the frequency content of these two things by taking their Fourier transforms, this one would have more high frequency content than this one, because it requires the high frequency content to reproduce the detail that you see here. Sharp, you know, things like sharp edges and things like that are associated with high frequencies. Okay. So the point here is that, you know, we can talk about these things, and we will talk about these things in both of these ways. And they are kind of just two sides of the same coin. Okay, there's just kind of different ways of looking at it, looking at this from different perspectives. The last thing I just wanted to point out, because, and this is important just because medical imaging systems are complex and have a lot of parts to them, is one other important result from linear systems theory is that, you know, if I have a system that could be broken down into a cascade of subsystems, okay, then in the frequency domain, I can just represent that thing as the product of their, well, in this case, OTFs, right? Product of their transfer functions. I'll just say transfer function. Okay, and so if we have a situation where, you know, these three guys have, these three elements of the system have different frequency responses. And so H1, let's say, looks like that, and H2 looks like that, H3 looks like that, roughly. The point here is, okay, well, the net response of this system is going to be the product of those three things, but there's a bottleneck, right? I mean, the one that really determines the ultimate response of the system, oops, sorry, is number 2, because it has the most limited frequency response. It doesn't really matter that, for example, it doesn't really matter that H1 passes these guys, because they're just going to get blocked by H2. Right? That's more or less what we're trying to express here. And so as a result, The whole point of kind of thinking about things in terms of a cascaded system is, look, if I have a complex system that's got several subsystems contributing to its overall transfer function, if I go and try to improve, let's say, subsystem 3 without doing anything to subsystem 2, it's not going to help a lot. So let's say I can do something wonderful and make subsystem 3 improve its frequency response at the higher frequencies. Well, that's not going to make a whole lot of difference to the net because system 2 is still there. Okay. So, you know, I should spend my time working on the weakest link if I want to improve the frequency response of the system. Okay. Again, that's kind of common sense, but it's worth thinking about, especially in terms of these types of systems, because there are a lot of elements to them. Well, that more or less addresses the question that I just asked here. Okay. All right. So that actually concludes the set of slides that were associated with the last course. We'll stop there for a moment and see if anyone has any questions. Okay, everything's cool. All right. So part 2 of introductory stuff is going to be a little bit more on Fourier transform. Okay, so again, you know, when we used a book, I used U and V as frequency variables to be consistent with what was in the book, and this is often used. As I said last time, and if a couple of you took my image processing course, I sometimes like to use omega X and omega Y to keep track of which is associated with which direction. That is not that hard, right? X, Y, U, V. Okay, that's not bad. And making note that in this form, where we have the 2 pi here to account for the radian component, the units of U and V are going to be cycles per unit distance, depending on what the units of X and Y are. So, right, X and Y are spatial domain measurement. And again, that's often pixels, but doesn't have to be. And so U and V basically have to be inverse to that, and so become cycles per unit distance. Okay. If we, you know, again, if we were to kind of look at the units of what goes on up in here, you know, basically we're talking about 2 pi radians per cycle times, let's say, I'll just use U. The same applies for V. Cycles per distance and times X, which is just in units of distance. Okay, whatever the units of distance happen to be. And so, you know, as a result of that, we end up with units of radians, which is what we should have here because this is a complex sinusoid. Okay. Okay. So hopefully, you know, the units make sense, and you know, we should just be aware of that. Okay. So the rest of today is mostly going to be about talking about some kind of, well, again, some of the things we use to kind of describe or compare imaging systems, and some of the concepts of things like resolution and contrast and noise. And so those are the things I want to talk about a little bit. First of all, if we think about any of these imaging systems, you know, it has a bunch of components, and if you kind of go through, especially in this is in a medical context here, but basically we're observing the real world in some way, and so we have some acquisition system that gives us raw data, and then very often that is processed in some way into what I will call a raw image. And again, sometimes this is a direct, and there's not something else that goes on. But in things like ultrasound or MRI, the raw data is not in the form of an image. Okay. And so it has to be processed to create an image. And then the image goes into a display system, because, I mean, what's the point of generating images unless we're going to display them in some way for a person to look at them, okay? And so that image is displayed and traditionally observed by a human, which leads to some diagnosis, treatment, judgment, etc. Okay. This could also all become a computer system, and there are some, but not many, limited examples of computers doing this job. Okay. A lot of times, well, the best examples are in microscopy, actually. For a lot of direct medical things, still humans are pretty closely involved. But like pap smears apparently were one of the first things that became done through automated analysis, because actually the computers turned out to be better than the people. Okay, so and we're seeing more and more of this, and so, you know, I'm not completely sold on how much actual like radiological diagnosis is going to end up being done by computers, because radiologists don't really want to be put out of business, and they're very good at what they do anyway. And there are relatively few cases of computers actually beating trained radiologists. Computers sometimes beat untrained radiologists, but not well trained and experienced radiologists. So anyway, so the whole imaging system is this train, really, and a big part of it is the display component. So, you know, we kind of have to think about all of these things contributing in some way to, let's say, the quality or the usefulness or the accuracy of what we get at the end of the pipeline. Okay, so as we talked about, right, a signal has two independent variables. They're spatial, and the dependent variable is intensity. And we said we kind of left that general because it depends on the imaging system specifically. So an imaging system, to be useful, okay, has to be sensitive to those things. Okay, in other words, it has to have spatial sensitivity. In other words, it has to give us some idea of where things are relative to other things. Otherwise, it's not really an image. Okay. And so, you know, that's its sensitivity along the independent axes. And then it also has to have sensitivity in the intensity portion, that is the dependent axis or axes. And another way of kind of expressing that is to say, to be useful, an imaging system has to be able to communicate that a feature exists, that it's different from the background, right? In other words, if an imaging system basically can't show that the intensity of the thing we want to see is different than the thing that surrounds it, not useful, because you can't see it. Okay, so the feature has to communicate that the feature is there and that it stands out from the background, and it has to communicate where it is, because that's the point of imaging, right? Is to be able to see where things are relative to other things. And so the sensitivity, so some of the measures that we express in talking about imaging systems address those issues directly. So the first one, so, and basically in general, these are contrast and resolution. So contrast refers to the intensity axis aspect of that. In other words, the degree to which a feature differs in intensity from its surrounding features, right? Or from its background. And so we need, we need that to be good, whatever we define good as, in order to be able to see things. It also has to have what we're going to refer to as spatial resolution. In other words, the precision with which it represents the position of a feature, or I should probably say it's not just position, but shape, detail, etc. Basically all of the things that can accurately represent things about that feature, and that refers to sensitivity along the spatial axes, right? So we can break it down that way. So I want to talk about each of these guys and what we mean by that, because we're going to, as we talk about individual imaging systems, we're going to kind of discuss, okay, what is contrast in that, and where does the contrast come from, and what makes some things have more contrast than others. There are a lot of different, I'm sorry, do we have a question? Yeah.
This is like going back a little bit, and it's more of a your opinion question, but do you think we lose like valuable data when we're optimizing for the human eye? I mean, like we're optimizing for a display. It could be CAD, but most likely we're going to optimize for like what we can see. Are we losing any significant amount of data by doing that?
Well, the answer is yes. And so actually, this is something I've talked a lot about lately. And so, well, since you've asked the question, I'm going to just give my philosophy on this. So there's a ton of research out there in trying to get computer systems to do what radiologists do. In other words, view images and make qualitative observations about them. Okay, and remember that a radiologist is usually doing things qualitatively, but it's based on a lot of experience and training and so forth. So it's not to say there's anything wrong with that. Okay, that's the way most radiologists are trained, and that's the way they work, and they're really, really good at it. And so I think there's limited value in training computers to do what radiologists already do pretty well. Can they do it better? Maybe in some cases, yes. And so that's fine. And, I mean, people will do that and so forth. But I'm personally not that interested in that. What's more interesting to me is training computers to do the things that the radiologists can't do, okay, which is going to be much more data oriented. And so from the standpoint of, so things like, and this is a thing that we work on some, integrating image data from different modalities and doing it quantitatively, which is the thing that computers are very good at and people are not as good at, right? And so, to go back to your question, well, are we losing things by optimizing for observation? Well, not necessarily if observation is the task, okay? And if that's what we're going to do with the image, that's fine, right? And when we probably should do that. But you are leaving data on the table, okay? Now it's data that would be much more difficult for a person to integrate, but computers could be very good at that. So that's my kind of general philosophy about, if you want to call it computer vision, or artificial intelligence as applied to this application. There you have it.
Yeah.
So I think I'm kind of agreeing with you in a sense, but again, one of the things that is very important in the imaging world, and actually has been looked at a lot by the FDA, who approves medical devices and therefore studies imaging systems, is that you really have to evaluate your system in the way it's going to be used. And so if the system is going to be used to present an image to a human, then it should be optimized for that.
And I guess some people might have reservations because it seems like a black box approach. At least when we optimize for the human eye, we can kind of confirm that that's what we're looking at. When we have data processed by a computer, we have less confirmation, I suppose, on that, which might make people more nervous.
Yeah, and so that's the other thing, but that kind of goes to, in general, how do you deal with the general problem in any artificial intelligence application of verifying that it's giving you the right answer, right? And so that takes a lot of careful study. And so I'll just give you an example of a study that we are just starting. We just finally got the final IRB approval to go ahead and recruit patients. We're doing a study to do combined PET MRI imaging of patients with kidney tumors. And we're basically going to evaluate some quantitative methods to kind of predict subclasses of the cancer. I'm way oversimplifying this, but because I don't have time. But how do we confirm the subclassifications of the cancer? Well, we have to wait till after surgery. They're going to freeze samples. We're going to do RNA sequencing on the samples in order to determine, what the genetic subclassification of those tissues is. And so we will have, gold standard data from that, but we're going to have to wait a while before we get it. Okay. So that's the kind of thing where it can be really, really hard to get the gold standard data you need in order to be able to prove that your system works. I mean, the other way you can do it is with long-term outcomes. If you say, okay, I'm going to have my computer system make a kind of a risk assessment, let's say on a cancer, and say this set of patients that, or my computer system will put you into a high risk or low risk category, and then after 5 years we see what the 5-year survival is, and if it correlates well, then you have a winner. But you have to wait 5 years for that, right? So those are hard studies to do. That's part of my point.
For sure.
Okay. Any other questions? Okay. All right. So contrast. When we talk about contrast, again, we're talking about this, and there's a lot of different mathematical definitions, because a lot of times you do a study, you have an object, you want to calculate its contrast, right? And so there are kind of different twists on this, but it's basically the idea is, okay, what's the difference in the object and the background relative to the background? Okay. And you can look in a lot of different places. So there's not one, my point is, there's not one standard definition of what this is mathematically. If you were to write a paper where you used contrast, you better define what you did as contrast, because everybody's not going to know just by you're using the word contrast. But in general, right, the idea is to express how well the thing stands out from its background. So in a simple case, we have this little circle phantom. And if we look at a profile here, we see that the big circle is about 0.6 and the background, its immediate background is 0.5. And so, it's 20% contrast, 0.2 or 20%. So that's a relatively simple calculation. We can have negative contrast also, and sometimes people will use an absolute value here, sometimes not, so they might call it a negative 0.2, or if it's understood that it's cold contrast or negative contrast, just again express it as a positive, that's fine. One thing to point out though is that because of blurring, right, this one doesn't look quite so flat here, and so if I was to say, okay, well, I could take, the minimum point as a contrast with that, but that's just looking at one pixel. And so, we might prefer to define some boundaries for what we think the object is and kind of average its intensity. And if we did that, we might actually be averaging values over some range here, let's say from here to here. And the average of those is going to come out to some contrast less than this, right? So blurring and object size can affect contrast. These things are not independent of each other, I guess is part of my point. So spatial resolution has some impact on the apparent contrast of an object. Okay. And the other thing is, if you're actually looking at an image, then where do you say, okay, what are the boundaries of that thing for which I am going to compute contrast? And that's a common problem with not really a great solution. Okay, you just kind of have to pick a way to do it and decide, what the boundaries of, these are nice, regularly shaped flat objects, but in medical context, you don't have that. And so you need some criteria. Sometimes they'll take the maximum and take a 50% of the maximum as a way of defining the boundaries of the object and then compute the contrast within that. But it's a little arbitrary. And, that's the way it's done. If you're doing research, as long as you're consistent, you're probably fine. Okay, here's this is a display trick. So essentially, these are this image where we have hot objects and this image where we have cold objects on the same background of 0.5, but they look different when I display them. Why? Does anybody have a thought on that? So over here, white is 0.5. Over here, gray is 0.5. The reason is because I've mapped them to the display with different scales. Okay, and this is very common. The default behavior of most display things is to say, okay, what's the maximum value in the image? In this case, it's 0.5. What's the minimum value in the image? It's 0. And then take all the gray levels I have available, black to white, and just move them between those. But here the maximum is actually higher, right? And so the gray levels are scaled between 0 and 0.6. So they have actually different grayscale mappings. And so this is important because the absolute contrast in the image, doesn't change, right? The values of, my quote intensities of those things in the original raw data are the same, but I can manipulate the contrast with which they are displayed, and I can do it very easily. And so here These are both renditions of the same raw image, but I have changed the grayscale mapping. So this is 0.5, this almost very dark gray, and this is 0.5, this almost very light gray in this case. And so if we were to look at that kind of in a maybe more formal way, this is often called a lookup table. And the idea is, of course, your display system requires you to take all your pixels and scale them, and I'm just talking about monochromatic right now. And so, your raw image can be, let's say, from 0 to, I don't know, let's just use an example of some very large number here, but we do get this in PET that actually has a physical measurement. So let's say our raw image ranges from 0 to 30,000, but our display system basically has 8 bits to work with. So it goes from 0 to 255, no matter what the input image I'm trying to display is. And so 0 is black, 255 is white, and then I have all of those gray levels in between. So I have to basically take whatever the range of my raw image is and map it into that display, which, among other things, impacts the dynamic range that I have, right? In other words, whatever the detail in this image happens to be, I can only display it at 256 gray levels. Okay. And so, a way of kind of expressing that is through a lookup table, which we might plot this way, like as a mapping function, right? And basically, my input intensities would go from 0 in that example to 30,000, but my output has to go from 0 to 255. And so in a straight linear mapping, which is kind of the default like that, basically all I do is I say, okay, I have a pixel here, I have a pixel here with an intensity of, let's say, 20,000. So it's going to be displayed with the appropriate intensity from just looking that thing up. Okay. Now, the point of manipulating the display intensities is this doesn't have to be a straight line. Okay. And so I can do something like this instead, where I essentially, anything, if I use my 0 to 30,000 example, anything up to 25,000 is all black. And I use my 0 to 255 to look at differences in this range. Okay, so this is the idea of kind of the dynamic range of the system. Now, one thing about this is the display intensity can be manipulated interactively very fast. And I think, as I mentioned before, radiologists do this intuitively. And so if you watch a radiologist kind of reviewing images on a screen, they're using their mouse to constantly change this thing and change the dynamic range and so forth in order to bring out different details at different intensities and so forth. Okay. And so, by the way, this kind of mapping would go with this case. Right. So you can, you can play tricks with the contrast. That's my point, if the point is displaying, but you do pay a price, right? In other words, we've totally blacked out all of these intensities in order to focus on these intensities. But that's, that's okay, because it can be done very fast and so forth. And so that's not a problem. So usually these things are, linear maps or piecewise linear maps, but they could be curves too. You can do them, look up tables that look like this, or like that, or whatever, right? So, okay. So as a result, if you might have two image values that are relatively close together, but you can kind of expand the contrast between those by manipulating this. The price you pay, of course, is that you saturate other things. And so, we're kind of talking in terms of, okay, in the piecewise linear case, the saturation, we've basically saturated to black all of these things in order to bring out contrast between those intensities. And that's the price you pay, but it's not a very big price because, again, you can change it in an instant. So just as a reference to linear shift invariant systems, is the piecewise linear mapping an LSI system? No, it's not. In fact, the only one that's a linear shift invariant system is this one, where you do a direct linear mapping. Any of these others is a nonlinear system. And so, again, we can't really analyze that element as a linear shift invariant system, but we probably don't, worry about that too much. Okay. Any questions on that? Does that all make sense? You will hear reference to contrast resolution sometimes. And, that is kind of expressing the ability of an imaging system to distinguish between two intensities that are close together. You could think of it as like the smallest difference in intensity between objects that a system detects as being different. Okay, and again, depending on what the system is. Humans can only resolve about 30 to 50 gray levels in a particular scene, but we are very adaptive. Okay, and so you can then go back to ask the question, well, okay, if I only have 255 gray levels in a normal display system, is that enough? And the answer is, well, yeah, actually, because we're only capable of doing that much at any given time. But the high function displays, very expensive displays that radiologists use not 8 bits of gray level, but 10 or 12 bits of gray level, which sounds like overkill because we can't see that much at any one time. But because we adapt to the local intensities, it does kind of allow for avoiding saturation of different parts of the image. And so, especially like in looking at mammograms and things like that, it is probably useful from a workflow point of view, but from a strict psychophysical point of view, if I was just to look at an image with a gray level image with 8 bits of gray level versus 10 or 12 bits of gray level, I don't really see the difference in detail. You and I are not really able to do that. So when a human is part of the system, a human kind of introduces some bottlenecks and limitations into the whole thing. So that's interesting. But again, because we adapt so much, if you move from focusing on one part of the image to another, the 30 to 50 gray levels we can detect actually change. In other words, our mapping changes rapidly as we move and focus on different parts of the image. So, there are arguments for why 10 or 12 bits might be valuable, or it might just be that, the companies can sell those for a lot of money to radiology practices. Okay. And of course, computer displays are limited by how many bits are available for each pixel. Now, I'm not talking about color here because humans can detect actually a lot more colors than they can just gray levels. And so there are, some applications where color is used to kind of enhance this process also. But,
I have
we're
a
not going to.
question.
Yes, question.
So when I get CTs for processing after patients have been scanned, sometimes I'm able to pick scans that have contrast and other times they don't have contrast. So do not all images go through this contrast process, or like?
Well, so in the CT context, I think they're talking about contrast media, in other words, iodine injection.
Okay, so something injected. All right.
Yes, yes.
That's what I thought it was originally, and then after we've been talking about all this, I was wondering if it maybe was something else.
No, yeah, and so actually it's a good point. I've never really made that connection. So in the medical application, okay, and we will actually talk about these things, but I should bring it up now. Sometimes we administer to the subject contrast medium, which is intended to provide extra contrast in detail in the images. So an example is iodine in X-ray and CT. Because the iodine stops more X-rays, it basically brings out the blood vessels, right? The vasculature. Same is true for gadolinium contrast in MRI. And so when physicians and technicians talk about it, they will refer to that as contrast, but they should be saying contrast medium. Well, not that they should be saying. What they mean is contrast media. Basically something you introduce to enhance the contrast of things in the image. Okay?
Makes a lot more, yeah, makes a lot more sense. It also explains why I had vessels show up as bone once.
Yeah, okay, yeah, because usually bone is the brightest thing, but if you introduce iodine in there, that's pretty bright too, right?
Well, awesome. Thanks for explaining that.
Sure. Good point. Okay. And so the idea of contrast resolution kind of leads us into spatial resolution with the idea that, okay, you have to be a little bit careful when you say resolution. What do you mean by that? Because this is not the same thing as this, right? They're on different axes. This is the intensity axis. This is the spatial axis. Usually when we say resolution, we mean spatial resolution. And then if people are talking about contrast resolution, they say the whole thing. They say contrast resolution. So be aware of that. But the idea is similar, right? When we say resolution, we mean, okay, what level of detail can we get with respect to that axis of the system? So again, the contrast or intensity axis or the spatial axis. Spatial resolution is a property of the point spread function and or MTF, right? They're related. They express the same thing in different ways. And so again, if we have a linear shift invariant system, the measures of spatial resolution are going to be based on these things. And it's going to turn out that even if we don't have a linear shift invariant system, we use modifications or things closely related to those to express it. Okay, now one thing I should point out is that a lot of times we talk about high resolution, right? We hear that with respect to televisions and things like that. And by high we mean, generally we mean better. However, I try not to say this. I might slip up once or twice, but I really try not to say that because it depends on, and only because it depends on how you're measuring it. And there's different ways of measuring this. And sometimes it's better to be high in that measure and sometimes better to be lower in that measure. So I tend to try to say better or worse resolution rather than high or low resolution. So just be aware of that. Again, usually if we say high resolution, we know we mean better, but we'll be a little bit careful with that. Okay, so these are the same guys as before, right? And so, you know, if we say, okay, which one has better spatial resolution, I say, okay, if these are the point spread functions, then they're going to blur the system with this function. And the one that introduces less blurring overall is going to have the better spatial resolution. So in a point spread function, narrower is better, right? Okay. And by the way, again, I could be tricking you, but I'm not, by using different grayscale displays for these two things and just making this look narrower. This is why, and again, not everybody does this, but if you like put images into a paper and, you know, put them in and do that, you probably should give it a grayscale bar. That's a way of doing this. This grayscale bar applies to both in this case. And so they're both on the same grayscale mapping. That's what that's meant to represent. Okay. Anyway, not tricking you there. This one really does look like this. Okay. So we would say narrower PSF is better spatial resolution, right? In terms of the MTF, though, we're in the frequency domain, so the opposite's going to be true. Okay. In other words, a wider MTF, which corresponds with a narrower PSF, is going to represent better spatial resolution because it has better response at high frequencies. Does that make sense to everybody? Okay, so again, it's two sides of the same coin. We can look at it either way. And we could express measures of resolution in either of these domains, and do, in fact. Okay, so I should point out that in general, you know, a real world imaging system will tend to act like a low pass filter. In other words, it's going to have better response at lower frequencies and worse response at higher frequencies. And so they will tend to have MTFs that look like this because of physical limitations and other things. Again, I say most, just to qualify it. Among other things, we can design digital filters, certainly, that don't. So, you know, not a real world physical system, but a mathematical system. We can design whatever filter we want to have in that. And, you know, in optics, certainly you can play tricks and do various kinds of weird Fourier optics and do weird stuff. So I'm kind of excluding that idea also. Okay, but with medical imaging systems, this is almost always the case. Okay, well, if you have a linear shift invariant system, then that's all you need to know. And so that's your complete characterization of spatial resolution, either the PSF or the MTF. That's all you need. If you have a linear but shift variant system, how do you characterize that? Well, you still have impulse responses. Let me go back to, let's say, here. If this is the point spread function, let's say for system one, and let's say this is linear and shift variant, well, that, you know, one way of looking at that is to say that, oh, okay, the point spread function is different in different places. Okay, and so it spreads more here and here, and somewhat less here and here, and maybe the least in the middle. Okay, whereas if it was shift invariant, these would all be the same. Okay, so if I put a point in at this location, it spread this much. If I put a point in at this location, it spread this much. So a linear shift variant system would have different point spread functions, or the point spread function is a function of location. Okay, and so you would need some way to characterize that, you know, and again, to completely characterize it, you need a point spread function for each position. But if we were just like doing measurements, we would say, okay, we take a measurement in the middle, we take a measurement at, let's say, 5 centimeters from the middle radius and maybe 10 centimeters of the middle radius. We take we take a point spread function at a couple of different locations and try to express how the point spread function changes with different locations. In other words, we're sort of pretending that it's kind of locally shift invariant. So, within close regions, it acts shift invariant, but over broad distances, it changes. If you have a nonlinear system, generally, you're still going to pretend it's linear and, measure the point spread function here and here and here for a particular object and try to express it in a similar sort of way. So you're still trying to kind of express things in terms of a point spread function or maybe a local MTF. Okay. The abbreviated way of characterizing, and I'll step back and say, to completely characterize it, you need the whole PSF, right? But that's a lot to try to communicate. And so in an abbreviated way, we often use full width at half maximum of the point spread function. So you get the point spread function, you find the peak, you take half of the peak and measure how wide it is at that point. So as a result, since this is in the spatial domain, it's a point spread function, the units of full width half maximum are spatial units. They could be pixels, they could be millimeters, they could be centimeters. And so this expresses the spatial resolution in a very intuitive way, right? If I say, oh, the spatial resolution of this PET system is about 4 millimeters, then that should express to you that, you know what, any details less than 4 millimeters, I'm not going to be able to see. Okay. So, this is often used because it really expresses it kind of very directly in ways that make sense. And it's relatively easy to, evaluate. If you have an estimate of a way of kind of measuring the point spread function or something close to the point spread function, then you can measure this pretty readily. Now, that doesn't tell you everything, right? We've abbreviated this whole point spread function into one number in that case. If the PSF is not isotropic, and by isotropic we mean same in all directions, so these guys are isotropic. In other words, they're radially symmetric, but if you had a point spread function, and this happens in real systems, that was like that, not the same in all directions, then you have you have to say, okay, how am I going to address that with full width half maximum? Well, I can say along one direction or along another direction, maybe the radial and the tangential direction kind of thing, or I can give the worst case. There's ways around that, but understanding that this isn't perfect and doesn't tell you everything. Also, especially in X-ray systems, right? Things like scatter give you these tails that stretch out but are very low valued, and it doesn't express anything about that, but those can have a big effect on how your image looks. But because they're below the halfway point, you wouldn't express them in full width half maximum. Sometimes people will do full width 10th maximum, so they'll take 1/10 of the peak to try to express that kind of thing. Okay. So the important thing I want to say is that this is often used. It's actually very good, and it's very easy to communicate to someone through this, but it doesn't incorporate all of the information that's there. Okay. Any questions on that? I think time's up as far as our scheduled class. So I'm going to end it there for today. But I'll stay on till everybody's gone in case there are any additional questions and so forth. So thanks for joining us. We'll see you on Tuesday. Feel free to exit if you don't have any other questions.
Thank you.
Bye-bye.
Thank you for the class. I'm figuring out how to exit. I don't have any other
Okay.
questions. Still new to Zoom.
I think if you go to the bottom of the
Oh, there it is. Yep.
screen, you'll get your meeting controls.
Awesome. Thank you. Have a good day.
All right, we'll see you.